Okay, now we're going to do my magic trick. Before we do my magic trick, we need to do some physics first. What we're going to do is we're going to look at this block and we're going to analyze the situation for this block. For a little while, we are going to ignore the pieces of thread and all that stuff. We'll bring that in when we do the magic trick, and I will make it very clear when I'm doing the magic trick and when I'm not. So at the beginning here, we're going to be doing physics. This is stuff that we're going to do repeatedly. When we do the magic trick, I will specifically identify. So we have the block. The block has a mass of 214.2 grams. We also need that in kilograms, so 1,000 grams on the bottom, 1 kilogram on the top. Grams cancel out. We get 0.2142 kilograms. We also need the angle of the incline. In order to get the angle of the incline, we're going to take some measurements. The first measurement is going to be the hypotenuse. The hypotenuse is going to be, I'm just going to go with 1 meter here because that's easiest. And then, let's try this again. Go 1 meter, which is right there. And then we have along the hypotenuse here, 19.9 is the height. So we have for our triangle 1.00 meters, and the height is 19.9 centimeters, which is the same thing as 0.199 meters. And we can figure out theta. Please figure out the incline angle for me. Mrs. Hong?
Sine theta equals after over hypotenuse equals 19.9.
Well, we should have them in the same dimension.
Oh, equals 0.199 over
Meters over
1.
Great. So we get that theta is equal to the inverse sine of 0.199 divided by 1. What is our incline angle?
11.4785 degrees.
Okay, 11.4785 degrees. That is our incline angle. Now we're going to draw the free body diagram of all the forces acting on this block while it is at rest on the incline here. Sam, give me a force in our free body diagram.
We have force.
All the forces acting on this block right here. Again, ignore the threads and stuff. We'll talk about that in a little bit.
No. We have force. Yeah, we do have force. I'm just kidding. We have force of friction. Right.
Which direction? Okay. Up the incline and parallel. What kind of friction?
We have
Static, because it's not moving. So we have the force of static friction acting up the incline. Another force in our free body diagram. Miss Stecker.
force of gravity. That's down.
Force of gravity is straight down. And another force. Laura?
Force normal, which is perpendicular to the surface, but up.
Force. This is our free body diagram. Step 1 is to draw the free body diagram. Step 2, class, is to? We'll try that again. Step 2. Could you hear? It was hard. Jessica, which forces do we need to break into components?
Force normal and force static friction.
If you look, the force normal and the force of static friction are neither in the x nor the y direction, so we need to break them into components. The force of gravity is straight down. Now, when we're on an incline, we're actually not going to approach it and solve it that way. What we're going to do is we're not going to talk about the x and the y axes. Instead, we're going to talk about an axis which is parallel to the incline and an axis which is perpendicular to the incline. So we're going to tip our axes, and rather than having x and y axis, we're going to have a parallel axis and a perpendicular axis. Looking at it in terms of the parallel and perpendicular axes, which forces do we need to break into components, Josh? The only one we need to break into components is the force of gravity. Rather than having to break up two, there's only one we need to break up into components. There's another reason we do this, which I'll talk about when we get a little bit farther into the class. So what we're going to do is we're going to break the force of gravity into the force of gravity perpendicular and the force of gravity parallel. Now, we need to figure out what this angle is right here. I'm going to call this theta 2. This one I'll call theta 3, and we can see that this is a 90-degree angle. This one I'll just call theta 1. So we have theta 1, theta 2, theta 3, and we know that's a right angle. If you look at this, we know that the inside angles of a triangle always add up to 180 degrees. So 180 degrees equals theta 1 plus 90 plus theta 3. Therefore, we can subtract 90 from both sides. We get 90 is equal to theta 1 plus theta 3. Therefore, theta 1 is equal to 90 minus theta 3 by just subtracting theta 3 from both sides. In addition to that, we can see that theta 2 plus theta 3 actually add up to 90 degrees. So 90 is equal to theta 2 plus theta 3. Again, we can subtract theta 3 from both sides, and we get theta 2 is equal to 90 minus theta 3. Therefore, what is true? Completely?
Theta 1 equals theta 2.
Notice theta 1 is equal to 90 minus theta 3, and so is theta 2. So theta 1 and theta 2 are the same angle. The point here being that the angle we're going to use to break the force of gravity into its parallel and perpendicular directions is the same as the angle of the incline.
Is that always true?
And that is always true. We're basically doing a derivation right now of force of gravity parallel and perpendicular. This is always true.
Does that mean to do that little set thing?
Give me just a little bit. I'll tell you exactly what you need to do in just a minute. Okay, so the force of gravity parallel we need to break into components, please. Emma, break the force of gravity into its perpendicular and parallel components.
Okay, sine of theta equals opposite over hypotenuse.
Opposite?
Force of gravity parallel.
Hypotenuse.
Force of gravity.
So we can multiply the force of gravity by both sides. We get that the force of gravity parallel is equal to the force of gravity times the sine of theta. And we know then that the force of gravity parallel is equal to mg times the sine of theta, because we know the force of gravity is equal to mass times the acceleration due to gravity. We can do the same thing with cosine. Cosine of theta equals adjacent over hypotenuse, where adjacent is the force of gravity perpendicular divided by the hypotenuse, which is the force of gravity. Therefore, the force of gravity perpendicular is equal to the force of gravity times a cosine of theta, or the force of gravity perpendicular equals mg times a cosine of theta. So what we have just done is derived the equations for force of gravity parallel and force of gravity perpendicular. We are going to deal with inclines so much that I am going to box these two equations. So on a quiz or final exam, you will get the equations for the force of gravity parallel and force of gravity perpendicular, where the force of gravity parallel is mg sine theta, and the force of gravity perpendicular is mg cosine theta, and the theta is the angle of the incline. Step 1 is to draw the free body diagram. Step 2 is to break forces into components. Class, what is step 3? Redraw the free body diagram. So here we have our block. We have the force normal, force of kinetic friction, the force of gravity perpendicular, and the force of gravity parallel. Now, I haven't really said what we're doing yet in this problem, so what I'll tell you is that all we're doing at the moment is figuring out all the forces so that we understand the situation. Then I'm going to do the magic trick. So we've drawn our free body diagram. We have broken forces into components. We have redrawn the free body diagram. Cosine, what is our next step?
Do we need to sum the forces in the x and y, well, in the parallel and perpendicular.
So now, rather than talking about the x and the y direction, we're summing the forces in the parallel and perpendicular direction. So please sum the forces in the perpendicular direction for me, David.
Force gravity, perpendicular, force normal, force gravity, perpendicular, negative. And that's acceleration. Force gravity, perpendicular.
What is the acceleration of the block in the perpendicular direction, Kraus?
0.
0. No, it's not moving at all, so the acceleration is equal to 0. So we get mass times 0 equals 0. So negative force of gravity perpendicular plus the force normal equals 0. In other words, the force normal is equal to the force of gravity perpendicular, which equals mg cosine theta. Class, does the force normal equal the force of gravity in this case?
No.
Try that again. Class, does the force normal equal the force of gravity?
No.
No, it equals the force of gravity perpendicular. It equals mg cosine theta. You guys get in the habit of thinking the force normal equals the force of gravity. It does not. You need to draw free body diagrams and sum the forces in order to figure out what the force normal is equal to. We do have numbers, so we're going to plug those in at this time. So we have mass, which is 0.2142 times the acceleration due to gravity at 9.8 times the cosine of our angle, which we got to be 11.4785 degrees. Therefore, we get the force normal equals the force of gravity perpendicular, which is equal to 2.075.
0572.
0572, I got those. In other words, with sig figs, 2.06 newtons. We draw the free body diagram. We broke forces into components. We redrew the free body diagram. We summed the forces in the perpendicular direction. Connie, what are we going to do now?
We're going to sum the forces in the other direction.
What's the other direction?
Parallel.
In the parallel direction. Go ahead, Con.
So it's going to be the static force of friction, oh no, kinetic force of friction minus the force of gravity in the parallel direction, which equals the okay, that equals to the force of kinetic friction minus.
We're gonna that's over here. What's the sum of the forces is always equal to?
Oh, mass and acceleration.
Why is it kinetic friction?
I don't know. That's what she said.
Oh,
It
sorry.
says like kinetic.
You wrote kinetic.
It's entirely possible that I wrote it down. I apologize. Sorry. It's static. I'm sorry. We were stuck here.
Acceleration is parallel.
Great. Acceleration in the parallel direction. Okay. What is the acceleration in the parallel direction, Con?
0.
0 because it's static friction. So we get that the force of static friction minus the force of gravity parallel equals 0. Therefore, the force of static friction is equal to the force of gravity parallel, which equals mg sine theta. We have numbers for all that. 0.2142 times 9.8 times the sine of our angle, which was 4785 degrees. The force of static friction is the same in magnitude as the force of gravity parallel, which equals
Wait, what? What did you say?
I need the number here.
Oh.
with sig figs 0.418 newtons. So what we've done so far is pretty typical of a way we're going to solve one of these problems. We've drawn a free body diagram, we followed all the steps, we figured out the values for the force normal, force of gravity perpendicular, force of static friction, and force of gravity parallel. What I'm going to do now is the magic trick. So let me reiterate that the magic trick we're about to do is not something we're going to do again in this class. Sure, if you want to perform this for your friends and family, you can do that at a later date. But the magic trick portion is not something we're going to do in the class. Again, we're only going to do this today. What we're going to do is we're going to start out by figuring out the mass in the perpendicular direction. The mass in the perpendicular direction is just going to be mass times the cosine of theta. Now, I'm going to use the mass in grams today. You'll see why in a moment. So the mass is 214.2 grams multiplied by the cosine of 11.4785 degrees. So could I please have the mass in the perpendicular direction? Plenty. So 210 newtons. So 2.10 times 10 to the second. I'm sorry, grams, not newtons. And we have the mass in the parallel direction, which is going to be at mass times the sine of theta, or 214.2 times the sine of 11.4785 degrees. Plenty. So 42.6 grams. All right. So for the magic trick, we have figured out that the mass in the perpendicular direction needs to be 42.6 grams. I only have increments of, my smallest one is 1 gram, so we're going to have to do 43 grams in the parallel direction, and we'll do 210 grams in the perpendicular direction. So I'll start with the parallel direction. We already have 5 grams in the parallel direction. So I add 20 in the parallel direction. We now have 25 grams in the parallel direction. We're going to add, so we have 25, add 10 more. We now have 35 grams in the parallel direction. We're trying to get to 43. So we have 35 plus 5 is 40. And then plus 2. 42 plus this little guy, plus 1, makes it 43 in the parallel direction. In the perpendicular direction, we already have 5. We need to get to 210. We now have 105. Adding 100 more will make it 205. Adding 5 more will make it 210. Now, it doesn't look like I've done much until I do this. Ladies and gentle people, I present for you a floating block. Look at that, will you? I will share something with it. It's a secret here, though. It's not actually magic. What did I do? I took the board away, and yet the block remains where it was. Heather?
Balance all the forces.
I balanced all the forces, right? Before, when the block was on the board, all the forces were balanced. But what I did is I replaced the force normal, for example, with this tension force. Because in the perpendicular direction, if you take your 210 grams in kilograms and multiply it by 9.8, you'll get the force normal, the same value. So rather than having the force normal, we have a force of tension in this string. Rather than having the force of static friction, we have a force of tension in this string. So what I did is I replaced the forces that the board was applying on the block, the force normal and the force of static friction, with two tension forces. And therefore, it turns out that the board in the end wasn't doing anything, so I was able to remove the board. And we now have a block in equilibrium, and it's floating. My favorite part, though, is if we do this. If I move it out of equilibrium and I let go, it will actually go back to the equilibrium position. Because if I move it out of the equilibrium position, it will have to accelerate back to that equilibrium position. And eventually it will go back, right back to where it was at the very beginning. It gives a very good visual of the direction of the force normal and the direction of the force of static friction. And darn it, it's a floating block.